This is video 2 of floating point numbers. Just give me a moment here, set things up. There we go. So let me just put a video 2. FPNs, if you will. Okay, and as promised, I want to go over some of the previous examples where I asked you to normalize some numbers here. So the first one we had here was 23.875. Now, one of the things you may want to keep in mind, you would find this helpful. I'm going to draw a little table over here, and I'm going to say 1/2 is 0.5, and 1/4, 0.25, 1/8 is equal to 0.125, 1/16 is equal to 0.0625, 1/32. And one of the things we're going to start to notice here is that to come up with the binary representation of floating point numbers is easy when the fraction has some number k over 2 to the m. In other words, when we see a 2 or 4, an 8, a 16, a 32, a 64, ... in the denominator, things are going to be kind of easy. Things get harder when that's not the case, and we'll look at an example of that in a second. But the thing to realize, okay, when I come over here and I look at this, when I see 0.875, well, that's actually equal to 23.5 plus 1/4. I'm going to put parentheses here. I'm going to say plus. So 1/2 plus 1/4 would be 0.75, and plus 1/8, that would get me up to 875. So the 23, let's see, that's equal to a 16 plus a 4 plus a 2 plus a 1. So that's a 10111. And then when I come over here and the 0.875, whoops, 0.875, well, that's equal to 1/2 plus 1/4 plus 1/8. So that is equal to a 0.111. So this whole thing is 10111.111. And that's times 2 to the 0. And now we have to go ahead and we have to normalize. And remember what normalize means. It means we want one non-zero element to the left of the decimal point. We've got to move this decimal point over here. So that means that this is 2 to the 0. To move it over here would be 2 to the 1st. To move it over here would be 2 to the 2nd, 2 to the 3rd, 2 to the 4th. So it's 1.0111, and then I have these 3 ones, 111 times 2 to the 4th. So this is the answer. Okay. The second one we were asked to look at was 0.125. And again, notice that's a nice number. That's just equal to 1/8. So that is 0.1/2, 1/4, 1/8 times 2 to the 0. But again, now I need to normalize. And that is equal to, we'll do this out in steps. So that would be 1.11. Notice I've moved the decimal point over 1. times 2 to the minus 1, but that's equal to, oh, I'm sorry, let's stop right there. That is normalized right there. I have exactly one digit to the left of the decimal point. 1.11 times 2 to the minus 1. Okay, and again, if you want to just expand this out to check your work, well, remember, this is equal to 1 plus, that would be, oh, I've made a tremendous mistake here. It's 1/8. This is all wrong. Okay, this is equal to, remember, if this is an eighth, then this is equal to 0 halves plus 0 quarters plus 1/8. So this is wrong. Teachers made big mistake right here on a video. Okay, so this is actually equal to 0.001 times 2 to the 0. And now I have some work to do here. So this is equal to 0.01 times 2 to the minus 1, which is equal to 0.1 times 2 to the minus 2, which is equal to 1.0 times 2 to the minus 3. And that makes sense. This is the correct normalized answer. I hope you're still with me after my error. Let's do the third one. So the third one is 31.75. And again, we note that that's equal to 31 plus 1/2 plus 1/4. 31 is equal to 16 plus 8 is 24. Plus 4 is 28. Plus 2 is 30. Plus 1 is 31. And the 0.75 is equal to 1/2 plus 1/4. So putting these together, I've got 16, 8, 4, 2, 1, point, 1/2 and 1/4. That's 1/2 and 1/4. That's times 2 to the 0. So I've got to normalize this. That would put it at 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So that's 1.12345 times 2 to the fourth. Again, recognize this number right over here is 1 plus 1/2 plus 1/4 plus 1/8. That's this one. This would be a 16th, a 32nd, and a 64th. I think I've got that correct. That would be 1, 2, 3, 4, 5, 6. This would be 1, 2, 3, 4, 5, 6. But this is all times 2 to the fourth. 2 to the fourth, this number here is 16. So first of all, let's come over here and let's put these all over 64s. So that's 1 plus 32 over 64 plus 16 over 64 plus 8 over 64 plus 4 over 64 plus 2 over 64 plus 1 over 64. So if I come over here and I add all of these up, 32 plus 16 is 48, that's 56, that's 60, that's 63. So that's 1 and 63 over 64. Okay, and this whole thing is times 16. Okay, so what is this? Okay, well, this over here is 64 over 64, okay? And I'm adding to that 63 over 64, and I'm multiplying this whole thing times 16, okay? So what I can do is first of all, that's going to be 63 plus 64, and over here I get 16 over 64. Okay, this is just 1/4, so this is equal to 63 plus 64 over 4 is equal to 127 over 4. And if I go ahead and I divide this in there, well, 4 goes into 12 3 times, 4 goes into 7 1 times, with a remainder of 3. That's 31 3/4, which is exactly the number that we started with. Okay, so I hope that those problems were helpful. I want to do one more thing before I end this video. I want to show you that there are times that these numbers don't work out so well. And what I want to do, let me see, I need this table over here on the right. So I am going to do the following. There, we've got that there. Suppose you were asked to write 7.3 as a normalized floating point number. Now the 7 part is easy, that's just 1, 1, 1. But what about the 0.3? That's 3/10. Okay? And you go, what do I do about that? Well, think about it this way. I come over here and I've got a half, and I've got a quarter, and I've got an eighth, and I've got a 16th, and I've got a 32nd, and this goes on for quite a bit. So I have 0.3. Well, first of all, if I come over here and I can see, well, there is no 0.5 in 0.3, so this is a 0. Now 0.25, 0.3, yeah, there's one of those. But now what do I have left? So I was at 0.3, and now I subtract a 0.25, and what's left is a 0.05. So I come down, I've taken care of this one. Now I look at 0.125. Well, there is no 0.125 in here, so this is also a 0. I come over here and I go 0.0625. Well, that's 0.06. That's still bigger than 0.05, so there isn't one of those in here. 0.03125, that's a 32nd. There is one of those, but now I have this terrible subtraction I have to go through. So that is 0.03125, and this becomes 499, and this is a 10, so that's a 5, that's a 7, 9 take away 1 is 8, and that's a 1, and that's an O. So I'm left with that. So I have over here, here's 1 over 64, and I go, well, there is one of those there. So I'm going to have a 1 here, and now I'm going to have a 0.01565. Okay, and you can see that this is going to be a mess. There's no real nice pattern here. I'm never going to get a clean answer like when I'm looking at 1/4 or 7/8 or something like that. So basically, this number here is approximately equal to, there's my 7, and then I would have 0, 1, and then it's 0, 0, 1, 1, and then there's a whole bunch of other stuff that's going to be a bunch of zeros and ones. Is it going to repeat? It probably isn't going to repeat. It's probably going to be a mess. So all that we can say is that ultimately we're going to get an approximation here. Now remember, I indicated to you in the last video that we have 23 bits here. Okay, so if we have 23 bits here, you can see we're only here. This is 2 to the minus 1, minus 2, minus 3, minus 4. So we're going to get resolution down to 2 to the minus 23. Now that's a really small number, 2 to the minus 23. Okay, 1 over 2 to the 23, that would be in the area of several million. So this is several millionths, which means that ultimately we're going to be able to write this thing accurate to within several millionths. But the other point that I'm trying to make is would I ever ask a number like this on a quiz? No, I wouldn't. If you take a look, and I know that some of you have already, in the book at some of the problems, they ask you some that look like this. And I think what your author is attempting to show you is that you're only going to get an approximation. You're never going to get something nice and clean like we got on these examples that we worked on over here. So that's a very important point to keep in mind. Something like 7.3, that would never be asked on an examination. That's just a lot of grunt calculation, and there's really not a whole lot to learn. So I hope that that helped and cleared up some things. I believe in the book, at some point they asked you to write the floating point number for Avogadro's number. Again, I can see your author laughing as he made that problem up. That's a completely unrealistic problem, but it takes a little bit of thought before you realize it's unrealistic. And I think that that was probably his intent. Okay, we're almost done. It's time that we have to put this all together, and I will save that for the next video. So we'll see you later, folks.